Hello, welcome to Cosine Similarity Explained. I'm going to be talking about cosine similarity, giving you a geometric view of it, and then also talking about how it's applied in retrieval-augmented generation. So let me first talk about the dot product. So here's the dot product, v times w, and you could see that we could put a summation symbol on it and have it go from I equals 1 to n. And if we expand that, we could basically have v1 w1 plus v2 w2 plus vn wn. So the dot product is a similarity metric because it's high when two vectors have large values in the same direction. There's no problem though. The dot product is sensitive to magnitude. If you have two vectors pointing in the exact same direction, but one is much longer than the other, say a long document versus a short tweet containing the same word, the dot product will be huge. This can be misleading if you only care about the topic and not the length. So let's talk about vector length. So you can see that v, the magnitude of v is equal to ni square root of the summation of ni is equal to 1 vi squared. Now I'm going to be talking about cosine similarity. So we see the formula a times b is equal to the magnitude of a, magnitude of b, divided by, times cosine theta. If we rearrange the terms, we've got cosine theta is equal to a times b divided by the magnitudes of a and b, right? So the normalized dot product turns out to be the same as the cosine of the angle between two vectors, following from the definition of the dot product between two vectors a and b. So here's cosine v of w. So we've got v times w divided by the magnitudes of vw. And we've got what we saw earlier with the dot product and the vector length, right? So we've got the vector length of vi and wi in the denominator, and then we've got the dot product in the numerator. So values can range from -1 to 1, -1 being complete opposite and 1 being completely similar. So let's go through a quick example. Say we've got two vectors, one representing the word calculus and the other one representing the word statistics. So step one would be to calculate the dot product, which was the numerator, which we saw in the previous slide. And we'd multiply each entry in the vector in vector A with each entry in vector B. So we've got 10 times 8 plus 0 times 0 plus 0 times 2, and that would equal to 80. Now let's calculate the magnitudes of A and B. We've got 10 squared plus 0 squared plus 0 squared. We take the square root of that, 100, and that's 10. The magnitude of b is 8 squared plus 0 squared plus 2 squared. That's 64 plus 4. We get the square root of 68, and that's 8.25. Step 3 is cosine similarity. And we just basically take the dot product divided by the magnitudes, right? So we got 80 divided by 82.5, and that's 0.97. Now let's talk about the geometry behind cosine similarity, because I think it gives good intuition as to like how cosine similarity works. And it adds to the formulas that we just talked about. Now we see this axis, this three-dimensional axis, where we've got y in motion, x logic, and z in nature, right? So we've got a lot of words that could fall into any three of these categories. Now we see cosine at 14 degrees, right? We've got the word statistics and calculus, right, with these two vectors. And we see that these two vectors are very similar, right? It's 0.97. Okay, and that makes sense, right? Now we've got a cosine at 90 degrees with two words, geometry and forest, and the similarity is absolutely zero, right? Because geometry and forest, there's no real shared meaning. Now we've got cosine at 180 degrees, and that's basically the complete opposite, right? So we've got total chaos, negative 1.000, and then we've got rigorous proof as 100, right? So these are completely the opposite, and the similarity is negative 1. Now, if we had another two words like poetry and algorithm, right? These are also not very similar. We have a similarity metric of negative 0.643, and we can see the two vectors are different, right? So negative 0.8, 0.91 for poetry, and 0.9, 0.1, and 0 for algorithm. Now let's give an example of where cosine similarity is used. And it's the most popular use case is retrieval-augmented generation. So let's imagine a law firm with 50,000 contracts. We'd have to put that into a embedding model where each contract or paragraph or whatever unit of observation that we're interested in will have to be converted into vectors, right? Embeddings. Now, in our UI, we ask the question, what are the termination clauses in our 2024 tech vendor agreements? That question would also have to go into the embedding. And there would be an embedding vector that's created from that. From there, all of these vectors would go into a vector database. And cosine similarity, right, would be applied. Now, the vectors obviously would have to be converted to text. After that, we would pass it into our LLM. And then finally, we would get an answer. So that's what we would get within this whole process and how it would work. Thanks for watching. I hope you enjoyed this video.